Okay, here we have topic 6, energy, work and power. So, how important is energy? This is not required for your notes, but it's quite an interesting point that energy, there's a fixed amount at the start of the universe, and it hasn't changed since then, which is basically related to your conservation of energy. However, looking at the things like E equals mc squared that you did in IG, you can also see from that the idea that the mass and the energy of the solar universe is a fixed amount, and afterwards we've still got that amount, we just change it from one form to another, and that includes changing sizes of masses. What is energy? Energy is the stored ability to do some work. Well, if you think about something like a car that has kinetic energy, it's got this thing called energy. And because of that, it can create noise when it crashes, it can create sound and heat when it's trying to slow down. Because of this thing called energy, it's got the ability to do something else or get transferred into something else. What is it actually? You know, if you really look at the main thing, I mean, if you actually want to draw a picture of energy, that's something we can't really do. We know what it does, and we can look at it mathematically, but we don't really know how to draw it. Energy could be put into different categories. Now, this is just a simple sort of description of the different types of energy. So potential energy is a sort of a general classification where it's a energy that is unseen. You can't really see it. It's just there, and it can be used to do other things. So chemical potential energy, energy stored in chemicals or molecules that once they react with something else, they can release a different type of energy that was stored within them. So you could have like a exothermic reaction which creates heat. Find two examples. We're essentially just looking for some chemical reactions. Elastic potential energy, energy to stretching a bond. So if you had a spring, so spring or elastic, then you could get the elastic potential energy. So it's energy due to the deformation of the bonds and stored in those objects. If we looked at gravitational potential energy, okay, if you have a hill and you put something close to the top of the hill, it has the ability to roll down that hill and change its sort of gravitational potential energy into kinetic energy. So because of that height, it's got the possibility of doing something. Electrical potential energy, energy stored due to the motion of charges. So charges in a circuit can do something. Okay, so they can be used to do something because of the electric force between charges. You can get it to do something. Energy possessed by a moving mass is kinetic energy. Okay, so it's pretty an obvious one. But it's interesting to see that if something's going at constant velocity, it can be unchanging in space. It can keep going with that kinetic energy forever. Good idea is to check the dictionary for this sort of stuff. Okay, it's all in there. And yeah, particularly the one that I've created. So, carrying on. Is there any others? Well, how about thermal? Okay, thermal is essentially electromagnetic radiation, which is the same as light, but essentially this one is associated with heat. Okay, so anything that hot will give off thermal radiation. Sound, motion of particles due to sound. So the clue there is that there's motion and sound. We could say that there's sound energy. It's just a general description of kinetic energy and particles, kinetic energy and gravitational potential energy, or electric potential energy. So sound is a combination of many types of energies. That's why we call things sound energy. Light, what is light? Well, it's actually essentially energy. It's just a oscillating energy fields. Nuclear, that's you bond, the very center of an atom is where you can store nuclear energy, very powerful energy, usually associated with a strong force. Internal energy is inside an atom. And we will define this later on in the year. But essentially, it's the sum of the random kinetic and potential energies of the individual molecules of an object. Okay, so we'll do that later on in the year. Work done equals change in energy. Okay, so if we transform energy from kinetic energy into sound, then the work done is the measure of that change in energy from one form to another. However, the actual definition of work can be found in the dictionary. It's associated with this formula instead, okay? So we could say this, we could say work is said to be done when a force moves its point of application in the direction of the force. However, you could define it using the word equation, but you've got to be careful there. You should also write this thing bit here, the direction of the force is very important, okay? It's in the same line, as opposed to a moment, which was 90 degrees. Here we got the formula. Work equals force times displacement. Usually it could be S or it could be X, okay? It doesn't really matter, but work equals force times displacement, and you notice here that the displacement along here is in the same direction as the force along that way. What's a derived unit? Well, we could do a bit of revision, okay? So W equals Fs, okay? So force equals mass times acceleration. So we could put that into that, MAS. And so mass is kg, acceleration ms to negative 2, multiplied by another m, and so that gives you kg m squared s to negative 2. What's the SI unit? Well, it's just the joule. How big is the joule? Pretty small. Okay, if you eat a burger and have a look on the side, it's not the amount of energy in the burger is not mentioned in joules, it's mentioned in kilojoules. Okay, so joules are actually a pretty small value. Work is scalar quantity, so to match the definition we need to make sure that the force and distance are always in the same direction. So the displacement's along this way, force is up that way. We need to adjust one of them to make it the same direction. So in this case we could find that horizontal force. So what we got here is a horse pulls a barge along the canal as shown. Calculate the work done by the horse and the barge if it travels a distance of 2 meters along the river and the tension of the rope is 3,000 newtons. So the motion of the barge is only along in this direction here. That's the only direction that's quite important. So we actually need to find the force in that direction. Okay? The force going in this direction, let's say force down, that force is actually irrelevant in terms of the work done. Okay, it's not actually providing any work to, so there's no work done from that downwards force to the barge. Okay, no work to that barge. However, this force here is providing energy to the barge. Okay? What is that force doing? Don't really care. Okay? It's not providing work to the barge. Okay? The question is asking what work that is done by the horse on the barge. So, let's get rid of some of that. Make it a bit clearer. So we want to know that this horizontal force here in relation to that one there. Okay, so it's just a bit of trigonometry. You've got hypotenuse and you've got adjacent, so it's something to do with cosine. Okay, and there must be an angle beside that. And we're trying to find the force. And in this case, it's actually going to be a smaller value, so it must be multiplied by it. Okay, so do that. That's your force. Work will then be equal to force times displacement, where your displacement is equal to 2 meters. So it's going to be your answer to that first one multiplied by 2. And if you work it out, it's a bit of a mistake there. Shouldn't really be newtons, okay? It should be in joules, shouldn't it? So should be joules there, okay, not newtons. Bit of a mistake in my notes there, so be aware of that. So we'll leave it there, and we'll carry on again soon.
Music, please.